Hey, welcome back. In this video, we're going to take a step back and focus on a specific group of different types of functions: exponentials, logarithms, and inverse trig. I mean, really, we've seen many of these integrals already, but this will just give us a chance to play a little bit more with these functions and get more used to them, specifically logarithms and the inverse trig functions. These first two integrals we've already seen and talked a bit about, but we have the integral of e to the x. This is the easy one, which just becomes e to the x, which doesn't get affected by differentiation or integration. Very similarly, if we have an exponential of a different base, what we get out is that factor of a to the x, but we're dividing by this natural log of a. In this case, remember, a is a constant value in these exponentials, so this will just be dividing by a constant, and always with this plus c. So those are the exponentials. Now on to the logarithms. This will be a little bit counterintuitive because we're used to the integral of 1 over x being the natural log of x. If we actually take the integral of the natural log of x, what we end up getting is x times the natural log of x minus 1, which can also be written as x times the natural log of x minus x, obviously, plus c. So there we have the exponentials. Now on to the logarithmic integrals. In this case, we'll first talk about the natural log of x. You might be thinking this has something to do with 1 over x, but not really, because that's the integral of 1 over x equals the natural log. But we're taking the integral of the natural log. This ends up being x times the natural log of x minus 1 plus c. We don't have the tools quite yet to evaluate this, but we actually could do this with integration by parts, which is coming next. But then in the same way, if I'm going to take the natural log of, let's say, log base a, if I haven't mentioned it yet, the a in each of these cases is strictly, actually in all the cases that I'm going to use, is strictly a positive number. So if I have that, the integral of that, again, is very similar to this and uses part of this concept up here, but it's just x over this factor of natural log of a times the natural log of x minus 1 plus c. These are 4 important integrals, but really I think you need to focus your energies memorizing these for the natural exponential and the natural log. And then know that in each of these cases, you're just dividing by this factor of natural log of a, which is that non-natural base in each of these cases. All right, so now we have the exponentials and we have the logarithmic. Let's now talk about some important inverse trig functions. First of all, if we have this, the integral of d of x over the square root of a squared minus x squared. In this case, this is sine inverse of x over a plus c. This is a little bit more of a general form than we've seen previously, where we have this value. It's not just a 1. In that case, we just get this division inside of the sine inverse. And again, that should make sense following from we know the derivative of the sine inverse function. In a similar way, if we take the integral of this 1 over a squared plus x squared, hopefully you can see that this looks a bit like the tan inverse integral, and it is. In this case, what we're going to get is 1 over a tan inverse of x over a plus c. Important to note right here with these two formulas is the fact that this does not have a factor of 1 over a on the outside, and this does. But you'll see the role that this a squared is playing in each of these formulas. All right, and then finally, we'll look at the integral of 1 over x times the square root of x squared minus a squared. And this results in 1 over a secant inverse of x over a plus c. One thing you might be thinking at this point, well, why did we choose sine inverse, tangent inverse, and secant inverse? Where's cosine? Where's cotangent and all these other ones? And the important thing is to say is simply this. We choose these 3 to really understand and have memorized because they give us these 3 different unique forms that we can use. For sure, you could write the integral that results in cosine inverse, but if you remember from the derivatives, sine inverse and cosine inverse, their derivatives were the same except for the this factor of -1, meaning when you're doing integration, you actually don't ever have to really think about the cosine inverse. Just by applying a negative here or there, you can turn the problem into a sine inverse problem. All right, in the first example, we're going to do is find the indefinite integral of x times log base 2 of x squared. If you take a look at this for a second, you might realize that we're going to use that new substitution rule that we have. What I'm going to do is let u equal this x squared. So if u equals x squared, then we have that du dx equals 2x. And then I'm going to divide over this 2 to get a 1/2 over there and multiply this differential right there. So what I end up with is 1/2 du equals x dx. So then making the appropriate substitutions, this will turn into, so the x and dx get replaced with the 1/2 du. I'm put the 1/2 out here and I get a du, and this becomes a log base 2 of u. All right, then we've simplified this integral. Now we just need to evaluate this with this property right here. And so the natural log base 2 of u du, well, we got this 1/2 out here first, is x over natural log of a. So in this case, our x is this u. So it's u over the natural log a, in this case, is our base of 2. And then times the natural log of u minus 1 plus c. Then, as always, all I need to do now is replace my u with my x to answer the original questions in terms of x. So I'll clean this up a little bit. We see this is 1 plus u. U is x squared, so this is x squared on top over 2 natural log of 2 times the natural log of x squared minus 1 plus c. So again, there's really nothing new there. That's just kind of using that substitution rule, using this property, which is probably the first time we've been dealing with it so far. But we've shown that the integral of this expression right here, that function equals this. What I'm going to do, just for fun and kind of tie stuff together, I think it's important at this point, is so we integrated this indefinite integral and got to this, then it must hold, given the fundamental theorem of calculus, that if I take the derivative with respect to x of this, I'll end up with that original function. So that's what I want to show now, just really to check my answer and to verify, does this make sense as the indefinite integral of this statement right here? So again, to do my check, what I'm going to do is I'm going to differentiate this expression that was the result of this integration. And if I did it correct, the derivative of this should turn into this function right here. First things to say is when I take the derivative here, I've got these terms. This is going to be using the product rule. This is important. I could distribute the x squared. I'm not going to, just out of preference, but I'm going to have the product rule. This is just a constant that I'm going to pull out. It's a constant factor that I'm going to pull out and then multiply by the result. And this is just a constant term. When I take the derivative, I'll have this product rule going on, but this just goes to 0, right? That's why we added it at the end. It's no matter what number gets added on. If you differentiated to go backwards, this would go away with that differentiation. So what I get in this case is I'll pull this 1 over 2 natural log of 2 out front here. And then we have the product rule of these two terms right here. And so I'll take the derivative of x squared to get 2x, and then times this other factor, so natural log of x squared minus 1. And then I'm going to add that to the derivative of this. The derivative of that, so this is constant, just goes away. I get 1 over x squared. Chain rule says I multiply that by 2x. And then I need to multiply that by the other factor of x squared. And then things clean up pretty nice, as you'll see. I'm going to distribute this 2x through here. These x squareds cancel, so this term just becomes 2x. So what I'll have is 1 over 2 times the natural log of 2 times 2x natural log of x squared minus 2x, and this becomes all plus 2x. So I get that this minus 2x and plus 2x cancel out. So I'm left with here is 1 over 2 natural log of 2 2x times the natural log of x squared. So we've taken the derivative, and we might be thinking, well, this is kind of similar to this statement, but it's not the same. And to be quite honest, for the move I'm about to do, this is really why I wanted to do this check, is play with this change of base property. It's really important. I'll state it before I use it, but we have this change of base property that says if you have a statement, it'll say log of any base right here to some input, that is the same thing as the natural log of x over the natural log of b. And what I'm going to do in this case is I'm going to go this way with this formula right here. Specifically, what I'm going to do is interact these two. So what I'm going to do here is cancel these 2's. I'm going to write this x out front. I'm going to write this natural log of 2 underneath this. And you probably can see where this is going. So the 2's are gone. I have an x right here. I have the natural log of x squared over the natural log of 2. And this, by this change of base definition, is the same thing as x times the log base 2 of x squared. And so often in this section, just importantly to say, is that while these formulas probably won't blow your mind when you go to use them, they're just new properties of integrals. Really, these sections that we're dealing with these exponentials, logarithms, and inverse trig is to remind you of how those functions react. Because throughout the rest of this quarter, we're going to have them in applications or need to apply them in different ways. You just need to know all the little tricks. And this, in my mind, is one really important one. This change of base going both ways, or knowing at least that this is equal to this statement right here. All right, in the second example, we're being asked to integrate 1 over 5 plus 9x squared. Now, in this case, this is a good example of why we're using these inverse trig functions here. On its face value, this looks nothing to do with trig functions or inverse trig functions. But what we can see is that this is very close to the form of this. All I'm going to do is rewrite this 9x squared, just so you don't have to do this. You can do this in your head, but it makes it easier for me. I'm going to write this as 5 plus 3x squared. Then what I'm going to do is do a substitution with the 3x, and we've done this a little bit previously, but in this case now I have u equals 3x. Take the derivative with respect to x of both sides. I get du dx equals 3. I will divide by 3, multiply over that dx differential, and what I get is 1/3 du equals dx. This is a really important point to reiterate something we've talked about before. But in this case, you might be thinking, what I'm going to do is use a u substitution for 9x squared. The issue with that is when you go through this substitution process with 9x squared, importantly, you're going to get a factor of x out, right? So because the derivative of 9x squared is 18x. And we don't have x's that we can to use this substitution. When I do this move to here, and I'm now going to substitute 3x, because the substitution is of a linear expression right here, when I take the derivative, there is no variable that I'm going to be substituting with. I'll just get a constant. And that's useful because then constants don't mess with anything. Constants can just pull out of the integral. This gets pretty straightforward here. So now I'll take this 1/3 that I put in when I replace dx. I always put this out front. It just makes my life easier. And what I now have, so I replace that with du, and I have 5 plus u squared. Now, I'm going to employ this property for the tangent. Importantly, you'll notice is that a squared component, and you've seen this often in algebra, right? So this is a squared. So when I write this out, a is going to be the square root of this. And it's not a nice square root, but I can just simply write it. And so to use that formula right over there, I have this 1/3 out front here. Then I get a 1 over a. That'd be 1 over the square root of 5. Times the tangent inverse of u over the square root of 5 plus c. That's really all the hard work. All I'm going to do now is clean this up. I could rationalize these denominators, but I really don't feel like it. It doesn't really matter. It's not a huge deal in case we need it in an application, though I do need to replace this u. So I have the tangent inverse of u, which is 3x over the square root of 5 plus c. All right, and before we end, we got to play around with the definite integral, of course, with one of these. I also am going to talk about something I introduced recently, which is this even-odd property of integrals. In this case, I'm thinking I could use it because it's going from a negative a to a. And the statement I'm going to make right now is that this function right here is even. Meaning, so an even function again means that f of x is equal to f of negative x. Meaning if I plug in a negative value for x or a positive value, just opposites of each other, it always outputs the same thing. And my justification is this. First of all, cosine is by definition an even function. We have this property right here. So the cosine of x is the same thing as the cosine of negative x. So we get that for free. Sine is actually an odd function. So we have actually the negative sine of x, or the opposite of sine x, is equal to the sine of negative x. So we get this negative here, and again, this tells you that the sign is odd. Though if we square both sides of this, because we have sine squared in this statement, so this, when we square, the negative goes away. We'll get sine squared of x equals the sine squared of negative x. Meaning, in this case right here, these places where I'm inputting my variable, which is the important parts, those two pieces will output the same thing for negative or positive. And again, what that means is that this function right here then is even. And what that does for us, it's not huge here, but I want to show this because it is useful moving forward in different cases. That means I can, instead of integrating from negative pi over 3 to pi over 3, I can write this as 2 times the integral from 0 to pi over 3 of this same function. Part of the real fun of this problem right here, this looks like a normal trig function. It's actually going to end up being a sine inverse function. It has a bit of this form right here, but we don't have x squared. We have sine of x. And so what I'm going to do is, you might see, I'm going to substitute u equals sine of x. And again, I'm thinking that because the derivative of sine is this cosine factor I have up here. So I have du dx equals the cosine of x, which tells me that du equals the cosine of x dx. And I'll just jump in right away and make that substitution. Remember, I need to make the adjustment to these, which I'll do in half a second. But this becomes 2 times the integral, and I need to fix those bounds. The cosine of x dx gets replaced with my du. I'll just write it up here. And then I have the square root of 4 minus, and now u squared. So now I need to change my bounds here. So this right here will be the sine of pi over 3, the sine of pi over 3, checking our unit circle right. This is the square root of 3 over 2. So that's my upper bound here. And then sine of 0 I need to calculate, and we all know that the sine of 0 is 0. And so now I can use this property of this integral for the sine inverse for this. In this case, a is 2. It's not a weird, it's a square root of 4, but we get a nice number like 2. So let's do this. So I get this 2 times the sine inverse of u over 2. And we're going to evaluate that from root 3 over 2 to 0. So I get 2 times this, so I'll write this like 2 times, I'm going to plug in root 3 over 2 into this. When I do that, I get the sine inverse. Root 3 over 2 divided by 2 is the root 3 over 4. And then minus when I plug in 0 into this. And in fact, if you can see this, if I plug in 0 for u, I get the sine inverse of 0. But the sine inverse of 0 is 0 because the sine of 0 is 0. Hopefully it doesn't blow your mind at that point, but minus 0 is what this ends up being. And so the answer becomes 2 times the sine inverse of root 3 over 4. Plug that into my calculator, and what I got is that equals about, let's give this the approximation symbols here, of 0.89566. Really, that's it. This section isn't about new integration techniques. All it's doing is it's going to have some different properties of exponentials, of logarithms, of tangent, of inverse tangent, just to make sure before we really get into playing deeply with the integration for the rest of this quarter, that you remind yourself of all of these properties. Yes, you should know that the sine of pi over 3 is root 3 over 2. You should then know that the sine inverse of root 3 over 2 is pi over 3, and vice versa. There's a lot of different properties like that. Getting used to applying these, and again, a few of these are just being thrown at you. We will show how you can prove this fact using the integration by parts method that's coming up next. But for now, the game is, if you have these tables, if you have this table of these integrals, you should be able to apply them to more complex things. These inverse trig might seem to come out of left field, but they're beautiful. And the fact that you have problems that start and don't look anything like inverse trig functions, but because of the look of their derivatives, they can be really useful, and they are really useful for us moving forward.